Humanity can measure distances trillions of kilometers away in the universe with extraordinary precision. But for now, those distances still remain beyond our reach. We can calculate how far a star is from Earth to within a fraction of a percent. We can measure galaxies so distant that their light began traveling toward us billions of years before our planet even formed. We have mapped the structure of the universe across unimaginable scales. In purely scientific terms, the universe has become measurable, but measurability is not the same as accessibility. There is a fundamental difference between knowing where something is and being able to reach it, between calculating a distance and experiencing it, between observation and interaction. And nowhere is this difference more severe than in space. The unit that exposes this divide is one that most people think they already understand: the light year. Ask someone what a light year is, and the answer usually comes quickly. It is a distance, the distance light travels in 1 year. A large number, a technical term used by astronomers, something abstract, impressive, but ultimately harmless. That answer is correct. And at the same time, it is profoundly incomplete. Because the light year is not merely a unit of distance. It is a constraint, a boundary, a limit imposed not by engineering, economics, or political will, but by the structure of reality itself. When astronomers say a star is 4 light years away, they are not simply stating how far it is in space. They are stating how long information takes to travel, how long a message would be delayed, how long it would take for any response to return. They are describing a separation in time as much as in space. Distance and delay are inseparable. At small scales, this delay is negligible. It goes unnoticed. When you turn on a light in a room, the light reaches your eyes so quickly that it feels instantaneous. When you speak to someone across a table, sound takes a measurable amount of time to reach them. But the delay is so small that conversation feels immediate. At cosmic scales, that delay becomes dominant. It grows from seconds to minutes, from minutes to hours, from hours to years. Eventually, it grows so large that it fundamentally changes what communication means, what travel means, what connection means. And that is where the misconception begins. Most people think of a light year as a large number because they encounter it as a number. 4 light years, 50 light years, thousands of light years. The emphasis is on magnitude, not consequence. The assumption is that these distances are simply very large versions of distances we already understand. But cosmic distance does not scale linearly with human experience. There is a threshold beyond which distance stops being an extension of travel and becomes a barrier to interaction. A threshold beyond which delay reshapes causality. a threshold beyond which planning replaces reaction. Autonomy replaces control, and separation becomes permanent rather than temporary. The light year marks that threshold. It exists not because astronomers enjoy using unfamiliar units, but because familiar ones fail. Kilometers and miles become meaningless when numbers grow so large that the human mind can no longer differentiate between them. Writing out the distance to the nearest star in kilometers does not clarify understanding, it obscures it. The light year was created to solve a measurement problem, but in doing so, it revealed something far more unsettling. It revealed that the universe is not just large, it is structured in a way that isolates. This isolation is not philosophical, it is physical. Signals cannot travel faster than light. Information cannot arrive before it is sent. Causes cannot precede effects. These are not technological limitations that might be overcome with better engines or more powerful computers. They are fundamental constraints built into space and time. As a result, distance in the universe does more than separate objects. It separates moments. It separates decisions from outcomes. It separates civilizations from one another. Not just spatially, but historically. When we look at distant stars, we are not seeing them as they are now. We are seeing them as they were. The farther away they are, the deeper into the past we are observing. At large enough distances, observation becomes archaeology rather than perception. This has profound implications. It means that the universe is not a shared present. There is no single cosmic now. Different regions exist at different points in time relative to one another, connected only by light that takes years, centuries, or millennia to cross the gap. It also means that exploration, as we intuitively understand it, may not apply beyond a certain scale. On Earth, exploration implies movement, return, communication, and coordination. Expeditions send back information. Leaders issue instructions. Unexpected events are addressed in real time. Distance complicates these processes, but it does not eliminate them. In space, beyond the scale of light years, these assumptions break down. A message sent cannot be corrected once it is on its way. A decision made cannot be revised before its consequences unfold. A response arrives long after the situation that prompted it has changed. The farther we imagine going, the more rigid the timeline becomes. This raises uncomfortable questions about humanity's future beyond Earth. If the nearest stars are separated by years of delay, what does interstellar travel actually mean? If communication takes decades or centuries, what does coordination look like? If civilizations cannot interact in real time, what does contact even consist of? And if these limitations cannot be engineered away, what does that imply about expansion, exploration, and long-term survival? These are not speculative questions. They are consequences of the same physics that allows us to measure the universe so precisely. Understanding the light year means confronting these consequences directly. This video will do 4 things. First, it will explain why light years exist as a measurement at all, and why traditional units collapse at cosmic scales. Second, it will show how light years force us to rethink space and time as linked rather than separate concepts. Third, it will examine how light years impose hard limits on travel, communication, governance, and civilization beyond Earth. And finally, it will explore why understanding these limits changes how we see ourselves as a species, our ambitions, our vulnerabilities, and our place in the universe. This is not a story about science fiction. It is not about hypothetical technologies that bypass known laws of physics. It is about what the universe allows and what it does not. The emotional response this understanding produces is difficult to categorize. It is curiosity mixed with unease, awe mixed with constraint, empowerment through knowledge paired with the recognition of limits. Many people know the word light year. Far fewer understand its consequences. To reach that understanding, we cannot start at the edge of the universe. We have to start with what feels familiar, with distances that make sense, with scales our brains evolved to navigate. From there, we will move outward step by step, from everyday distances to planetary distances, from planetary distances to stellar distances, from stellar distances to galactic and intergalactic scales. At each stage, intuition will weaken. Assumptions will fail. The meaning of distance will shift. And eventually, distance will stop being about how far something is and start being about how isolated it is. Only then does the light year reveal what it truly represents. Not just how big the universe is, but how it separates, delays, and constrains everything within it. To understand why cosmic distance is so difficult to grasp, it is necessary to begin much closer to home, inside the limits of human perception itself. Human beings did not evolve to understand distance as an abstract numerical concept. Distance, for most of our evolutionary history, was not something to be calculated. It was something to be survived. Knowing how far something was mattered only insofar as it affected effort, time, and risk. For hundreds of thousands of years, human survival depended on 3 fundamental spatial abilities. The first was understanding walking distance. Early humans needed to know how far they could travel before exhaustion, dehydration, or darkness made movement dangerous. Distance was not measured in meters or kilometers, but in how long legs could carry a body at a sustainable pace. The critical question was never, how far is it? But, can we reach it before nightfall? The second was visual range. Human eyesight evolved to detect movement, landmarks, and threats within relatively short distances. Open savannas favored long sight lines, but even then, vision was measured in hundreds of meters, not tens of kilometers. Anything beyond the horizon simply did not exist in practical terms. If something could not be seen, it could not be acted upon. The third was seasonal travel. Migration routes, hunting grounds, and water sources were not defined by precise coordinates. They were defined by memory and repetition. Humans learned that food appeared in certain places at certain times of year. Distance, again, was understood as a pattern of effort repeated over time, not as an absolute measurement. Because of this, the earliest systems of measurement were inherently body-based. A step was not an abstract unit. It was a literal step. A day's journey was not a fixed distance. It was how far a group could travel between sunrise and sunset under typical conditions. Landmarks, trees, rivers, hills, rock formations served as reference points because they were visible, stable, and meaningful to navigation. These units worked because they were aligned with human capabilities. They mapped directly onto muscle fatigue, daylight availability, and memory. They did not require calculation. They required experience. As human societies became more complex, these informal measures gradually evolved into standardized ones. But even then, the logic remained the same. Early formal units of length were often derived from the human body: the foot, the cubit, the span of an outstretched arm. These were not arbitrary choices. They reflected a world where distance mattered only at scales humans could physically traverse. This alignment between measurement and survival is crucial. Measurement did not emerge to describe the universe. It emerged to help humans move through their environment safely and efficiently. Units were shaped by what humans needed to do, not by what existed beyond their reach. This is why distance feels intuitive on Earth. When someone tells you a location is 5 kilometers away, your brain automatically translates that number into time, effort, and experience. You imagine walking, driving, stopping, resting. You do not consciously calculate meters. You recall similar journeys. The number becomes meaningful because it fits within an evolutionary framework built around human-scale movement. The problem arises when measurement escapes that framework. As humans began to explore beyond local environments, across continents, across oceans, and eventually beyond the planet, the relationship between distance and direct experience weakened. Numbers grew larger, travel times stretched, landmarks disappeared, yet the measurement systems remained rooted in a human past. Kilometers, miles, and nautical miles are extensions of the same logic. Distance is accumulated human effort. They work well on Earth because Earth is small enough for effort-based intuition to remain valid. Space is not. The distances between celestial objects do not scale with human capabilities. There are no steps, no days of travel, no landmarks, no horizons that meaningfully divide the space between Earth and the stars. Movement through space does not resemble movement across land or sea. There is no gradual progression of experience that intuition can latch onto. This mismatch is not a failure of education or imagination. It is a consequence of evolution. Human cognition is optimized for survival within a narrow range of spatial and temporal scales. Beyond that range, intuition collapses. Numbers lose their connection to experience. Distance stops being something you can imagine doing and becomes something you can only describe. Understanding this limitation is essential before introducing cosmic distance. The difficulty people have with light years does not come from their size alone. It comes from the fact that they describe distances that have no evolutionary equivalent. There is nothing in human history, biology, or daily life that prepares the brain to interpret separation measured in years of light travel. Before we can understand why astronomers needed a unit like the light year, we must first recognize that our intuitive sense of distance was never designed for the universe at large. It was designed for survival on a single planet. Everything that follows builds on this constraint. The measurement systems humans use today feel objective and universal. Kilometers, miles, and nautical miles appear precise, standardized, and scientifically grounded. But these units did not emerge from an abstract need to describe reality at all scales. They are refinements of much older, experience-based systems designed to function within the boundaries of Earth. On our planet, these units work remarkably well. A kilometer or a mile corresponds to distances that can be walked, driven, or otherwise traversed within a meaningful span of time. Even when the numbers become large, hundreds or thousands of kilometers, they remain tied to recognizable experiences. A long road trip, a cross-country flight, or a journey around the globe can still be broken down into familiar segments. Hours of travel, refueling stops, changes in landscape, periods of rest. Distance remains connected to effort and time. This connection is what gives Earth-based measurement its intuitive power. When someone hears that two cities are 300 kilometers apart, the number does not stand alone. It immediately translates into a sense of duration, cost, and physical movement. The brain does not visualize 300,000 meters. It recalls similar trips. The unit works because it maps onto lived experience. That mapping collapses beyond planetary scales. Once distance extends beyond Earth, kilometers and miles lose their interpretive value. The numbers increase rapidly, but the human brain has no corresponding experience to attach to them. There is no journey, no sequence of events, no progression of effort that scales naturally from driving across a continent to crossing the space between planets or stars. At that point, numbers stop functioning as measures and start functioning as symbols. This leads to a phenomenon known as cognitive compression. When quantities exceed the range of direct or indirect experience, the brain compresses them into a single category. very large. The difference between millions, billions, and trillions becomes difficult to perceive intuitively. The numbers are distinct on paper, but they feel interchangeable in the mind. Psychological research on numerical cognition supports this. Humans are relatively good at distinguishing small quantities, and even moderately large ones, when those quantities relate to concrete objects or repeated experiences. But as numbers grow, especially beyond the thousands, precision deteriorates. The brain no longer processes magnitude linearly. Instead, it shifts to approximate grouping. This is why people often react similarly to figures that differ by orders of magnitude. 1,000,000, 1,000,000,000, and 1,000,000,000,000 are all understood as huge, even though the differences between them are enormous. Without a lived reference point, the brain cannot easily maintain proportional understanding. This limitation has nothing to do with intelligence or education. It is structural. Human cognition evolved to make rapid, practical judgments in environments where counting beyond small groups was rarely necessary. Estimating the size of a herd, the number of people in a group, or the amount of food available required rough accuracy, not numerical precision. Modern measurement pushes far beyond that evolutionary comfort zone. When astronomers describe the distance to a nearby star in kilometers, the result is a number so large that it ceases to communicate meaning. The digits can be written down and manipulated mathematically, but they do not inform intuition. They do not help the listener understand what that distance implies for travel, communication, or observation. This is where Earth-based units fail. They remain mathematically valid, but cognitively ineffective. They no longer convey scale in a way the human mind can process. Instead of clarifying understanding, they obscure it by overwhelming perception. The problem is not that kilometers are inaccurate. The problem is that accuracy without interpretability is not useful for comprehension. A unit that cannot be mentally related to experience does not function as a bridge between data and understanding. This limitation forced astronomers to adopt a different approach. Rather than measuring distance in terms of accumulated human movement, they needed a unit grounded in a universal constant, something that applies everywhere, regardless of location, technology, or observer. A unit that could scale with the universe itself, rather than with human capability. The solution was to tie distance to time through the one thing that connects all of space: light. Before introducing the light year, it is important to recognize why familiar units had to be abandoned. They did not fail because the universe is complicated. They failed because they were designed for a world that is small. Understanding that mismatch is essential. Without it, the light year appears arbitrary. With it, the light year becomes inevitable. Everything that follows builds on this shift, from distance as human effort to distance as physical constraint. For most of human history, the question of how far away the stars were could not be answered, not because people lacked curiosity, but because the universe offered no accessible clues. Early astronomy developed without any reliable way to measure depth beyond the solar system. As a result, stars were understood not as distant objects in three-dimensional space, but as fixed points projected onto a celestial backdrop. In ancient and medieval astronomy, the sky was effectively flat. Stars appeared to maintain the same relative positions night after night, year after year. They rose and set in predictable patterns. Constellations remained stable across generations. From the perspective of an observer on Earth, there was no visible indication that some stars might be closer than others. All stars seemed equally distant, embedded in a single, unmoving sphere surrounding the Earth. This perception shaped early cosmological models. In many early systems, stars were thought to be attached to a celestial sphere beyond the planets. Even after Earth was no longer considered the center of the universe, the idea of stellar depth remained elusive. The sun, moon, and planets showed obvious motion against the background of stars, but the stars themselves did not shift in any detectable way. Without observable motion relative to one another, there was no basis for estimating their distances. The core problem was not conceptual. It was observational. To measure distance in astronomy, one needs a reference effect, something that changes depending on the observer's position. On Earth, depth perception relies on parallax. Nearby objects appear to shift relative to distant ones when the observer moves. This effect is obvious at human scales. As you walk, nearby objects move quickly across your field of view, while distant objects barely shift at all. Astronomers understood this principle early on. If stars were at different distances, Earth's motion around the sun should cause nearby stars to shift slightly against the background of more distant stars over the course of a year. This phenomenon, known as stellar parallax, was theoretically sound. The problem was that the effect was too small to detect. Even the nearest stars are so distant that their parallax shifts are minuscule, far smaller than the resolving power of early instruments. For centuries, astronomers searched for stellar parallax and failed to find it. This absence was not interpreted as a limitation of measurement, but often as evidence that stars were either extremely distant or fixed to a rigid celestial sphere. In some historical models, the lack of parallax was used to argue against Earth's motion entirely. If Earth moved, stars should shift. Since they did not, Earth must be stationary. This reasoning was incorrect, but it was understandable given the available evidence. Instrumentation was the decisive limitation. Before the development of precision telescopes, micrometers, and stable observational platforms, astronomers simply could not measure angles small enough to detect stellar parallax. The shifts involved are measured in fractions of an arc second. Angles far beyond the capability of naked eye observation and early optical devices. As a result, stellar distance was not merely unknown, it was unknowable with the tools available at the time. This distinction matters. An unknown quantity is something that could, in principle, be measured but has not yet been. An unknowable quantity is one that cannot be measured given existing constraints. For most of history, the distances to stars fell into the second category. There was no experimental path forward. No refinement of existing methods could bridge the gap. This meant that early astronomy focused on motion, brightness, and position, not distance. Stars could be cataloged, named, and tracked across the sky, but their placement in three-dimensional space remained inaccessible. Brightness was sometimes assumed to correlate with proximity, but this assumption was unreliable. A bright star could be intrinsically luminous, but far away, while a dim star could be relatively close, but faint. Without distance, scale was absent. Astronomers could describe the structure of the solar system, but the universe beyond it remained effectively dimensionless. There was no sense of how large it was, how stars were distributed, or how separated they were from one another. The cosmos was vast in appearance, but undefined in extent. This changed only when measurement technology crossed a critical threshold. In the early 19th century, instruments became precise enough to detect stellar parallax for the first time. When astronomers finally measured the tiny annual shift of nearby stars, the implications were immediate and unsettling. The distances implied by those small angles were enormous, far larger than anyone had anticipated. The stars were not just farther away than the planets. They were separated by distances so vast that traditional units became impractical almost instantly. It was at this moment that astronomy encountered a new problem. Distance was no longer unknowable. It was measurable, but the numbers involved were so large that existing measurement systems failed to communicate what those distances actually meant. The universe had acquired depth, but human intuition had not caught up. The invention of the light year was not a conceptual leap forward, so much as a necessary response to this new reality. Once stellar distance became measurable, a new language was required to describe it, one that reflected not human movement, but the fundamental limits imposed by physics itself. Understanding this history is essential. The difficulty people have with light years today is not a failure of explanation. It is the legacy of a universe that revealed its scale only after humanity had already built its intuition around a much smaller world. Before light years, distance was invisible. After light years, distance became unavoidable. Without context, the light year often appears to be an arbitrary invention. To many people, it sounds like an unnecessary complication, a confusing blend of time and distance introduced by astronomers for their own convenience. The word itself reinforces this misunderstanding. The presence of year suggests time, while its actual purpose is to describe distance. Without explanation, the unit feels counterintuitive, even misleading. This reaction is not unreasonable. If the historical and cognitive constraints that led to the light year are ignored, the unit can seem like a poor choice rather than an inevitable one. Kilometers already exist. Miles already exist. Why introduce something new? Why tie distance to time at all? The answer lies in the structural problem astronomy faced once the scale of the universe became measurable. Light years were not invented to rename distance. They were invented because existing units could no longer perform their function. A unit of measurement is only useful if it communicates meaning. Once distances exceed the range of human intuition, numerical precision alone is insufficient. The number may be correct, but the understanding is lost. Astronomy reached a point where this breakdown became unavoidable. After stellar parallax made distances to nearby stars measurable, astronomers were confronted with figures so large that they could not be practically used or easily compared. Writing distances in kilometers produced strings of digits that conveyed little about relative scale. The difference between one star and another became buried in zeros. The units were mathematically accurate, but cognitively opaque. This was the structural failure the light year addressed. The problem was not naming, it was representation. Astronomers needed a unit that could scale with the universe while remaining interpretable. They needed a way to express distance that preserved proportional relationships and conveyed consequence, not just magnitude. By tying distance to the speed of light, the light year accomplished this in a way no Earth-based unit could. Light is not a human reference. It is a physical constant. Its speed is the same everywhere in the universe, and for all observers, regardless of motion or location. Using light as a basis for measurement removed the need to anchor patterns to human experience. Instead, distance was anchored to a universal process. Just as importantly, the light year embedded time directly into the concept of distance. This was not an aesthetic choice. It reflected a physical reality. At cosmic scales, distance cannot be separated from delay. Information, signals, and observations are constrained by how long light takes to travel. Any unit that ignores this connection is incomplete. The light year makes this constraint explicit. When a distance is expressed in light years, it immediately communicates two things: how far away an object is and how long its information has been in transit. A star that is 10 light years away is not just distant in space. It is separated by a minimum of 10 years of delay. That fact has consequences for observation, communication, and causality. Without this context, the light year looks like an odd hybrid. With context, it becomes the only unit that makes sense. Understanding why light years were invented changes how they are perceived. They are not a clever rebranding of distance. They are a response to the collapse of human-centered measurement at cosmic scales. They exist because the universe operates according to rules that do not scale with human intuition. This is why context matters. Without it, the light year feels abstract and detached. With it, the unit reveals the structure of the universe itself. It shows that scale is not just about size, but about limits on interaction, influence, and connection. Everything that follows in this discussion depends on recognizing this shift. The light year is not an optional tool. It is the language forced upon us by a universe that is far larger and far more constrained than human experience ever prepared us to understand. Only once this is clear can we move forward from the history of measurement to the consequences of scale. Before distance became an abstract quantity expressed in equations and scientific notation, it was a practical concern tied directly to movement. Human beings did not first understand distance by measuring it. They understood it by traveling through it. At the smallest scale, distance was experienced through walking. A short distance was one that could be covered on foot without strain. A longer distance was one that required rest, water, or daylight. The body itself became the measuring instrument. Muscles, breathing, fatigue, and time all combined to create an internal sense of how far something was. This sense did not require numbers. It relied on repetition and experience. As societies developed, driving and riding distances extended this framework rather than replacing it. Animals, carts, and eventually vehicles increased speed and reduced effort, but the logic remained the same. Distance was still understood in terms of time and exertion. A journey might take hours instead of days, but it was still segmented into recognizable phases: departure, travel, arrival. Roads provided continuity. Stops provided rhythm. The journey itself reinforced the scale. At larger scales, continental distances introduced complexity, but not abstraction. Traveling across a continent required planning, resources, and endurance. Yet it remained conceptually accessible. Maps showed routes. Cities marked progress. Even when the journey was long, it was still composed of smaller, understandable segments. Distance accumulated gradually through experience. Even the circumference of the Earth, while vast compared to daily travel, remains intuitive in a way that is often overlooked. Humans have circumnavigated the planet. Ships, aircraft, and satellites have followed continuous paths around it. The Earth is large, but it is finite and bounded. Its scale can be explored, measured, and repeated. Distance around the planet still implies a closed loop, a return, a completion. These distances remain intuitive because they are anchored to two fundamental correlations. The first is time correlation. On Earth, Distance almost always translates directly into duration. A longer distance means more time spent traveling. Even when speed varies, the relationship remains predictable. Humans are adept at estimating time, and time provides a familiar reference for understanding space. The second is effort correlation. Distance is felt physically. Whether walking, driving, or flying, movement requires energy. That energy expenditure reinforces scale. A journey that is exhausting feels long. A journey that is effortless feels short, even if the numerical distance is greater. The body plays a constant role in interpreting space. Together, time and effort create psychological anchoring. This anchoring is strengthened by memory. Humans remember journeys not as distances, but as sequences of actions and experiences. The road taken, the terrain crossed, the stops made along the way. These elements form a mental map. Distance becomes embedded in narrative. Movement creates memory, and memory gives distance meaning. This is why human scale distance feels manageable. It is not because the numbers are small, but because the experience is structured. There are pathways to follow, and landmarks to confirm progress. There is a sense of orientation. Even when the destination is far away, the journey itself provides constant feedback. This framework begins to fail when those elements disappear. The first crack appears when distance no longer has pathways. On Earth, movement is constrained by geography. Roads, rivers, coastlines, and air routes guide travel. They break distance into usable segments. In space, there are no roads. There are no routes etched into the environment. Movement does not follow terrain. It proceeds through empty volume. The second crack appears when distance no longer has landmarks. Landmarks provide reference points that confirm direction and progress. They reassure the traveler that movement is occurring and that orientation is maintained. In space, there are no intermediate markers between destinations. The space between objects is largely empty, offering no visual or physical cues. When distance lacks pathways and landmarks, it stops behaving like distance as humans understand it. Travel becomes a continuous state rather than a sequence. There is no sense of along the way. There is only departure and arrival, separated by long stretches of nothing. Memory has nothing to attach to. Effort becomes decoupled from progress. Time stretches without feedback. This is the moment where intuition begins to erode. Human-scaled distance relies on movement through structure. Cosmic distance is movement through absence. The tools the brain uses to interpret space, time estimation, effort assessment, memory formation, lose their effectiveness when there is nothing to interact with between 2 points. This is why scaling Earth-based distance outward eventually fails. The problem is not size alone. it is the loss of structure. Once distance becomes empty, continuous, and unsegmented, it stops being something humans can naturally comprehend. It becomes something that can be measured, but not experienced. This part establishes the baseline, distance, as humans evolved to understand it. Everything that follows represents a departure from this baseline, a progression into scales where distance no longer aligns with intuition, and where measurement must replace experience. The distance between Earth and the Moon marks the first point at which human intuition about distance begins to fail in a fundamental way. Numerically, it is not especially large when compared to cosmic scales, but psychologically, it represents a sharp break from every distance humans evolved to understand. The Earth-Moon distance is not just farther than any journey made before the modern era. It is different in kind. On Earth, distance is accompanied by structure. There are surfaces to move across, reference points to pass, and environmental changes that confirm progress. Between Earth and the Moon, none of these exist. The space separating the two bodies is almost entirely empty. There are no intermediate locations, no visual markers, no gradual transitions. Once a spacecraft leaves Earth orbit, there is nothing to interact with until it approaches the Moon. This absence of landmarks removes the feedback loop that normally supports intuition. Without reference points, movement becomes difficult to perceive. Distance loses texture. It no longer feels like something being crossed and becomes something being endured. This is why the Earth-Moon distance resists mental visualization. The number, approximately 384,000 kilometers, can be memorized. It can be written down, but it does not translate into experience. There is no journey humans can recall that resembles it. There is no route to imagine, no sequence of events to reconstruct. The distance exists as a quantity without narrative. The paradox becomes more apparent when travel time is introduced. The Apollo missions traveled to the Moon in about 3 days. That figure often surprises people. 3 days does not sound particularly long. Modern transportation routinely covers vast distances in far less time. Commercial flights cross continents in hours. Spacecraft move at speeds that exceed anything encountered in daily life. And yet, the journey still took 3 days. This exposes a critical disconnect between speed and intuition. The Apollo spacecraft reached speeds of roughly 11 kilometers per second. That is hundreds of times faster than highway travel. At such speeds, one might expect the Moon to feel close. Instead, it remained distant. Even at velocities that defy everyday comparison, the space between Earth and the Moon refused to collapse into something intuitively manageable. This is the travel time versus speed paradox. As speed increases beyond human scale experience, it stops enhancing intuition. Numbers grow larger, but understanding does not follow. Fast loses its meaning because it no longer relates to any familiar frame of reference. When everything is fast by human standards, speed alone cannot make distance feel smaller. At this point, the brain has no anchor. Movement is too rapid to be imagined, and distance is too empty to be segmented. The result is a cognitive gap where neither speed nor distance provides clarity. The journey becomes a duration without texture, measured only by clocks rather than experience. This paradox becomes even more pronounced when the scale expands beyond the Earth-Moon system. The distance between Earth and the Sun is approximately 150 million kilometers. This number is commonly cited, but rarely understood. It is not just large, it is cognitively inert. The brain cannot meaningfully differentiate it from other very large numbers because there is no experiential framework to support it. Unlike continental distances, the Earth-Sun separation cannot be associated with routes, rest points, or environmental variation. There is no sense of progression from here to there. The number does not imply effort or duration in any intuitive way. Even when travel time is calculated, intuition does not recover. At the speeds achieved by Apollo-era spacecraft, reaching the distance of the Sun would take several months. At the speeds of the fastest modern probes, it would still take weeks to months. These durations are long, but they do not correspond to any familiar type of journey. They exist outside the range of human-scale travel narratives. This is why the number itself fails cognitively. The Earth-Sun distance introduces a scale where numbers no longer inform understanding. They communicate magnitude, but not meaning. The relationship between speed, time, and distance becomes abstract rather than experiential. At this stage, a pattern emerges. Even at extraordinary speeds, distance does not collapse into familiarity. Even at this speed, the journey remains long. Even at this speed, the destination feels remote. Repeating this realization reinforces a critical insight. Increasing speed does not restore intuition once distance exceeds a certain threshold. This repetition is not rhetorical. It reflects a physical reality. As distances grow, speed becomes less relevant to comprehension. What matters is the absence of intermediate structure and the inevitability of delay. The brain is forced to confront the fact that some separations cannot be made intuitive, regardless of how fast the traveler moves. The Earth-Moon distance is where this confrontation begins. It is the first distance that cannot be reconciled with human-scale understanding. It marks the boundary where distance stops being something that can be imagined through movement and becomes something that must be accepted through measurement alone. Beyond this boundary, intuition does not just weaken, it breaks. The next step in scale makes that break permanent. Once distance extends beyond the scale of planets, a fundamental problem emerges. human-centered references, walking, driving, even spacecraft velocity, no longer provide a stable foundation for understanding separation. At that point, astronomy requires a reference that does not depend on biology, technology, or perspective. That reference is light. Light is used not because it is convenient, but because it is universal. Everywhere in the universe, light behaves the same way. It does not matter where it is measured, who measures it, or how fast the observer is moving. Light travels at a single, fixed speed through empty space. This speed does not vary with location, direction, or motion. It is the same near Earth, near distant stars, and in the space between galaxies. This constancy is not an approximation. It is a foundational property of reality. Crucially, light's speed is independent of observer motion. In everyday life, speeds add together. If you move forward on a train and throw an object ahead of you, someone standing on the ground sees the object's speed as the combination of both motions. This logic holds for cars, planes, and projectiles. It does not hold for light. If an observer moves toward a light source, they do not measure light traveling faster. If an observer moves away from it, they do not measure light traveling slower. Every observer, regardless of motion, measures the same speed. This behavior defies everyday intuition, but it has been confirmed repeatedly through experiment. It is not a quirk of measurement. It is a property of space-time itself. This makes light uniquely suited for measurement. Because its speed never changes, light provides a reference that is completely detached from human experience. It does not depend on muscle strength, fuel efficiency, engineering limits, or sensory perception. It is not anchored to what humans can do. It is anchored to how the universe operates. This distinction matters. When distance is measured using human-scale units, interpretation depends on context. A kilometer means something different depending on terrain, speed, and effort. Even time-based units like hours or days are tied to human activity cycles. They reflect how humans move through the world. Light removes this subjectivity. By anchoring distance to the speed of light, measurement is grounded in physics rather than experience. A light-based unit does not care whether a distance feels long or short. It only reflects how long it takes information to travel through space. This shift eliminates human bias from the measurement itself. It also reveals something essential about large-scale distance. Distance is inseparable from delay. At small scales, this delay is negligible. At cosmic scales, it becomes dominant. Light does not arrive instantaneously. It takes time to cross space, and that time cannot be reduced. No signal, message, or observation can arrive faster than light. This has 3 immediate and unavoidable consequences. The first is communication delay. Any attempt to communicate across large distances must contend with the finite speed of light. Messages sent across space cannot be instantaneous. They arrive only after a delay proportional to distance. As distance increases, conversation transitions from interaction to exchange and eventually to historical record. The second is observation delay. When we observe distant objects, we are not seeing them as they are in the present. We are seeing them as they were when their light began its journey. Observation becomes a look into the past, with the delay growing longer the farther away the object is. The third is cause and effect delay. Actions taken in one location cannot influence distant locations immediately. Effects follow causes only after light has had time to travel. At large enough distances, this delay reshapes planning, response, and coordination. Decisions must be made without feedback, and corrections arrive too late to influence outcomes. These delays are not technological shortcomings. They are built into the structure of the universe. Even a perfect communication system, operating at the maximum speed allowed by physics, cannot bypass them. This is why light is used as the foundation for cosmic measurement. It does not merely describe how far away something is. It describes how separated it is in time. It encodes the minimum delay between events. It defines the boundaries of interaction. By anchoring distance to light, astronomy aligns measurement with reality rather than intuition. The result is a unit that is initially unsettling, but ultimately unavoidable. Once distance exceeds human scale experience, the only meaningful way to describe separation is in terms of how long the universe itself takes to transmit information. That realization prepares the ground for the next step, turning the speed of light into a unit of distance, and confronting what that unit implies when scaled across the cosmos. Once distance is anchored to the speed of light, a new challenge emerges. The numbers involved grow rapidly, far beyond anything encountered in daily life. At this point, the limitation is no longer measurement. It is comprehension. The human brain does not process large magnitudes intuitively. At small scales, numerical differences are easy to grasp. The difference between one object and 5 objects is immediately obvious. The difference between 10 and 20 can be estimated quickly. Even differences in the hundreds or thousands can be understood when they relate to concrete items, repeated actions, or familiar contexts. Beyond that range, perception begins to collapse. This is especially evident when comparing 1,000,000, 1,000,000,000, and 1,000,000,000,000. On paper, these quantities are clearly distinct. Each represents a 1,000-fold increase over the previous one. In practical terms, however, the brain often treats them as variations of the same idea, very large. This collapse occurs because magnitude outpaces experience. There is nothing in daily life that requires direct interaction with millions or billions of discrete items. Without repeated exposure or physical reference, the brain has no intuitive framework for maintaining proportional differences at that scale. Instead of scaling linearly, understanding becomes logarithmic. Differences are compressed. Precision is lost. This is why numerical distance expressed in raw figures becomes ineffective at cosmic scales. Writing out trillions of kilometers communicates accuracy, but not meaning. The digits accumulate, but intuition does not follow. One of the few reliable ways to restore comprehension is to translate magnitude into time. Time-based framing serves as a cognitive workaround because humans are deeply attuned to duration. Unlike large spatial quantities, time is experienced continuously. Days, years, and lifetimes form the backbone of memory and planning. When large numbers are converted into time, they regain structure. Counting examples make this clear. Saving 1 unit per day, it takes years to reach a modest total. Saving 1 unit per second accelerates accumulation dramatically. The difference between these two rates is easy to understand because time provides a familiar rhythm. Seconds, minutes, hours, and years are lived experiences, not abstractions. As numbers grow, time reveals their true scale. Historical anchoring extends this approach further. When quantities are tied to known periods in human history, they become meaningful again. A few thousand years spans recorded civilization. Tens of thousands of years reach back to the emergence of early human cultures. Hundreds of thousands of years extend into deep prehistory. Beyond that, even time begins to lose its anchoring. This illustrates a critical point. Magnitude destroys intuition, not because numbers are complex, but because they exceed the range of human reference. The brain is optimized for environments where differences mattered at small scales. It is not designed to track exponential growth across multiple orders of magnitude. In astronomy, this limitation becomes unavoidable. Distances measured in light, travel time quickly extend beyond centuries and millennia. At that scale, the delay between events exceeds the span of individual lives, recorded history, and even entire civilizations. Numbers that represent such distances no longer describe journeys or durations that can be mentally simulated. This is why light years feel unsettling. They combine two domains, distance and time, that both exceed human scale experience. A light year is not just a large number of kilometers. It is a year of delay at the fastest possible speed in the universe. Multiply that by tens, hundreds, or thousands, and the resulting separation no longer fits within any intuitive frame. The brain responds by flattening these distinctions. 10 light years and 100 light years both register as far. 1,000 and 1,000,000 light years both register as extremely far. The proportional difference exists mathematically, but it does not translate psychologically. This is not a failure of explanation. It is a cognitive boundary. Understanding cosmic distance, therefore, requires deliberate framing. It requires slowing down, breaking scale into steps, and repeatedly reconnecting numbers to processes the brain can follow. Without this effort, magnitude overwhelms intuition, and measurement loses meaning. Once the limitations of large numbers become clear, the only way forward is to rebuild scale gradually. Jumping directly from human-scale distances to light years overwhelms intuition and invites disengagement. To understand what a light year represents, distance must be constructed step by step, using light itself as the measuring tool. The progression begins with the smallest meaningful unit, the light second. A light second is the distance light travels in 1 second. Even this unit immediately exceeds most human-scale experiences. In a single second, light can circle the Earth multiple times. It can cross continents repeatedly. Compared to anything humans can physically move, a light second is already enormous. Yet it remains comprehensible because the time involved is familiar. 1 second is experienced constantly. It is short, immediate, and well understood. The distance covered in that second can be accepted because the duration is intuitive, even if the spatial extent is not. From there, the scale increases to light minutes. A light minute is 60 light seconds. This multiplication introduces the first serious strain on intuition. The time is still familiar. 1 minute passes quickly. But the accumulated distance grows beyond anything encountered in daily life. At this scale, the separation between Earth and the Sun becomes meaningful. Light takes several minutes to travel between them. For the first time, delay becomes noticeable. Despite this, the brain still attempts to compress the scale. 60 seconds does not feel like a dramatic increase. The temptation is to assume the distance has only grown modestly. This assumption does not survive further progression. A light hour multiplies the scale again. 60 light minutes compound into a distance that stretches beyond planetary orbits. The time involved, 1 hour, is still within everyday experience, but the spatial separation it represents has no terrestrial equivalent. At this stage, the progression becomes methodical by necessity. Incremental scaling matters because it prevents premature abstraction. Each step forces the brain to confront a concrete increase rather than glossing over magnitude. Skipping steps allows intuition to escape by treating all large distances as equivalent. Incremental progression removes that escape route. With each multiplication, the gap between time and distance widens. The duration remains manageable, but the space it spans becomes increasingly alien. This mismatch creates attention. The brain cannot rely on familiar heuristics. It must either accept the scale or disengage. The methodical buildup does not allow disengagement. Each step compounds the previous one. Light seconds lead naturally to light minutes. Light minutes lead to light hours. There is no abrupt leap, no sudden jump that can be dismissed as hypothetical. The scale grows through repetition rather than surprise. This process creates psychological inevitability. At each stage, an intuitive shortcut is removed. The viewer can no longer say, "This is just a big number," because the number is built from small, familiar units. The accumulation is undeniable. The scale emerges not as an abstract concept, but as the logical outcome of repeated, understandable steps. By the time the progression reaches light days, light weeks, and eventually light years, compression becomes impossible. The brain can no longer flatten the scale without contradiction. The distance is too large, the delay too persistent, the structure too rigid. Each attempt to minimize the magnitude is undermined by the stepwise construction that led there. The result is unavoidable acceptance. The viewer is forced to confront a reality that cannot be simplified mentally. The scale cannot be made smaller by imagination. It cannot be reduced to a metaphor or dismissed as a large but generic quantity. It exists as a concrete accumulation of time-bound distance. This is the turning point. From this moment on, distance ceases to be something that can be intuitively compressed. It becomes something that must be reasoned about consciously. The light year no longer feels like an arbitrary unit. It feels like the only possible outcome of the universe's rules, applied repeatedly and without exception. With this foundation in place, the next realization follows naturally. Once distance is built from time in this way, observation itself becomes a form of time travel, and separation acquires a historical dimension that reshapes how the universe is perceived. Once distance is constructed from light travel, a fundamental transformation occurs. Distance is no longer just separation in space. It becomes separation in time. At human scales, this distinction is invisible. Light travels so quickly across everyday distances that delay is imperceptible. Seeing and knowing appear simultaneous. Observation feels present tense. The brain assumes immediacy because the delay is too small to register. At cosmic scales, that assumption collapses. Every observation of distant space is an observation of the past. Light carries information, and that information requires time to travel. The farther away an object is, the older the information becomes by the time it arrives. Distance is therefore inseparable from delay. Stars are not just luminous objects in space. They are historical records. When light leaves a star, it begins a journey that may last years, centuries, or millennia before reaching an observer. During that time, conditions at the source can change. The star may evolve, alter its output, or cease to exist entirely. None of those changes are visible until the information arrives. Observation does not reveal what is, it reveals what was. This is not a limitation of telescopes or sensors. It is a consequence of finite signal speed. No improvement in technology can eliminate this delay. At large distances, observation is fundamentally retrospective. Historical anchoring makes this effect concrete. When observing a star tens of light years away, the information received predates recent human history. Events that appear current in the sky occurred long before modern technologies existed. Observing stars hundreds of light years away reaches back before the industrial era. Thousands of light years extend into periods when written language had not yet emerged. These alignments are not symbolic, they are literal. The photons entering an observer's instruments today began their journey at moments that coincide with specific eras in human development. The sky becomes layered with different epochs, each star representing a distinct moment in time, rather than a simultaneous present. This is why intuition struggles. On Earth, seeing and happening are effectively aligned. Across interstellar distances, that alignment breaks. The brain expects perception to reflect current conditions, but cosmic observation violates that expectation consistently. The deeper the observation reaches into space, the further it reaches into the past. At a certain scale, present tense observation becomes impossible. There is no way to see a distant object as it exists now, because now cannot propagate across space instantaneously. The present collapses into a local phenomenon. This leads to a critical realization. Space and time cannot be separated operationally. In principle, they may be treated as distinct concepts. In practice, when dealing with large distances, they function as a single constraint. Measuring where something is automatically specifies when its information originated. Location implies age. This fusion has practical consequences. Any attempt to interact across large distances must contend with temporal separation. Responses arrive too late to influence events directly. Coordination becomes prediction rather than feedback. Decisions must be made without current information. At this point, distance is no longer a passive property. It actively shapes what is possible. The light year embodies this transformation. It is not merely a unit of distance. It is a measure of temporal separation enforced by physics. Each light year added increases the minimum delay between cause and effect by a year. This reframing changes the role of scale entirely. Large distances are not just farther away, they are further back in time. The universe does not present itself as a single moment spread across space. It presents itself as a layered record of its own history, accessible only through delayed information. Understanding this prepares the viewer for the next shift in perspective. Once distance and time are fused, separation becomes more than physical. It becomes social, informational, and eventually civilizational. That is where the implications of light years extend beyond astronomy and into the structure of human possibility itself. The recognition of isolation and limitation often invites a mistaken conclusion. The constraints imposed by light years render human effort insignificant. This conclusion follows naturally from scale comparisons, but it does not survive careful examination. Limitation does not eliminate meaning, it reshapes it. The universe does not assign significance based on size, reach, or longevity. Meaning emerges from processes that occur locally within the constraints that exist. Human civilization operates within a narrow window of space and time, but within that window it demonstrates an unusual capacity, the ability to understand its environment. Knowledge is the differentiator. Unlike most physical systems, human societies do not merely react to conditions. They observe, model, and predict. They build representations of reality that extend far beyond direct experience. Through measurement and inference, they reconstruct events that occurred long before they existed, and in regions they will never visit. Light years limit travel and communication, but they do not limit comprehension. Even when physical access is impossible, information can still be gathered. Observation allows reconstruction of distant processes. Mathematical frameworks allow extrapolation beyond immediate perception. Instruments translate faint signals into structured data. The result is a form of reach that does not require presence. This distinction is critical. While civilizations may be isolated from one another, they are not isolated from the universe. The same physical laws operate everywhere. Understanding those laws allows local observers to infer global behavior. Each civilization, confined to its region, can nevertheless construct an accurate picture of the larger structure it inhabits. Meaning arises from this act of understanding. The value of knowledge does not depend on whether it can be shared instantly or acted upon universally. It lies in the capacity to explain, predict, and contextualize experience. Within a single star system, a civilization can comprehend phenomena spanning billions of light years and billions of years. Constraint sharpens this capacity rather than diminishing it. When reach is limited, observation becomes essential. Precision replaces expansion. Depth replaces breadth. Instead of dispersing across space, inquiry turns inward and outward simultaneously, mapping reality through theory rather than traversal. This reframes human significance. Humanity's role is not defined by how far it can travel or how many systems it can influence. It is defined by its ability to extract meaning from limited information, to build coherent models from delayed signals, and to understand a universe that vastly exceeds its physical reach. In this context, isolation becomes a condition rather than a verdict. Each civilization operates as a localized center of understanding. Even if no contact ever occurs, the act of comprehension itself retains value. Knowledge exists independently of its transmission. Discovery does not require witnesses beyond the discoverer. This perspective resolves the apparent tension between scale and significance. Light years impose constraints that cannot be overcome. They define boundaries on movement, communication, and coordination. But within those boundaries, the capacity for understanding remains intact. Meaning persists not in spite of limitation, but within it. With this framework established, the final task is synthesis, bringing together distance, time, isolation, and understanding into a coherent conclusion that leaves the viewer with a stable perspective rather than unease. That synthesis forms the closing argument. When distance is measured in light years, isolation is no longer an accident of geography. It becomes a structural condition imposed by physics. Civilizations separated by interstellar distances are not merely far apart. They are functionally independent. Independent development follows naturally from delay. Without real-time communication, coordination across star systems is impossible. Information arrives too late to guide decisions. Shared strategies cannot be adjusted collaboratively. Collective problem-solving collapses into parallel effort. Each civilization develops in relative isolation, shaped primarily by its local environment, resources, and historical contingencies. Even if two societies originate from a common source, divergence begins immediately, once separation exceeds the range of rapid feedback. This independence is not ideological, it is operational. Real-time cooperation requires synchronized awareness. It depends on the ability to observe outcomes, exchange responses, and adapt collectively. Light-year delays disrupt every element of that process. By the time information is exchanged, the conditions that generated it may no longer exist. As a result, cooperation becomes archival rather than interactive. Messages exchanged across interstellar distances function as records rather than conversations. They document past states rather than current needs. They inform understanding, but cannot support joint action. Planning must assume uncertainty rather than reduce it. This has profound implications for civilizational behavior, technological development, ethical norms, governance structures, and cultural values evolve without external correction or alignment. Each society becomes a local solution to local problems. Even if contact occurs, it does not reverse this process. The exchange of information may influence future directions, but it cannot synchronize present realities. Over long timescales, divergence becomes irreversible. Civilizations separated by light years accumulate differences, not only in technology, but in priorities and interpretations of reality. Shared origins lose relevance as local histories dominate identity. What remains is a loose conceptual kinship rather than a functional connection. This isolation also limits collective response to existential risks. Threats that operate on local scales must be addressed locally. There is no mechanism for coordinated defense, warning, or mitigation across interstellar distances within actionable timeframes. Each civilization confronts hazards alone, relying on its own foresight and resilience. The absence of real-time cooperation does not imply stagnation. On the contrary, independent development encourages diversity. Solutions vary. Knowledge branches. Innovation proceeds along multiple, uncoordinated paths. The universe becomes a mosaic of separate experiments rather than a unified project. This perspective reframes the idea of cosmic community. Instead of imagining a network of civilizations interacting across the stars, the structure imposed by light years suggests a landscape of isolated islands. Each island may be rich, complex, and internally connected, but externally separated by delays that cannot be bridged. Understanding this isolation clarifies why interstellar influence remains limited, even in a universe that may contain many advanced societies. It also sets the stage for the final reflection. If connection is constrained, then the significance of each civilization lies not in its reach, but in its capacity to understand and preserve what it learns. That realization leads directly into the concluding perspective on meaning, responsibility, and perspective at cosmic scales. The vast distances defined by light years reshape one of the most persistent questions in modern science. If the universe is so large and old, why does it appear silent? This question is often framed as a paradox. Given the number of stars, the prevalence of planets, and the apparent ease with which life emerged on Earth, many assume that intelligent civilizations should be common. If they are common, the argument continues. Signs of their existence should be detectable. The absence of such signs is frequently interpreted as evidence of rarity or non-existence. This interpretation overlooks the structural role of distance. Silence does not imply absence. It may instead reflect separation. When distances between stars are measured in light years, communication becomes inherently delayed and attenuated. Signals weaken as they spread. Detection requires alignment in time, direction, and frequency. Even deliberate transmissions become difficult to identify across interstellar space. Accidental leakage, such as routine radio emissions, disperses rapidly and fades into background noise. Distance acts as a filter. Only signals that are both powerful and precisely targeted are likely to be detectable beyond a narrow local region. Even then, detection depends on timing. A transmission sent for a limited period may pass through a region of space long before another civilization develops the capability to observe it. Temporal mismatch compounds spatial separation. Civilizations may exist at different times rather than merely different places. A technological society could arise, transmit signals for a few centuries, and disappear long before those signals intersect with another observer. From the perspective of both, the universe remains silent. Distance, therefore, transforms the search for extraterrestrial intelligence into a problem of overlap rather than abundance. The relevant question is not how many civilizations exist, but how many exist close enough in space and synchronized enough in time to allow detectable interaction. Light-year separation reduces this overlap dramatically. This reframing dissolves the apparent paradox. The absence of detected signals does not require rare intelligence or self-destructive tendencies. It can be explained by the simple fact that the universe enforces isolation through scale. Even a galaxy filled with life could appear quiet when observed from any single location. Understanding this shifts expectations. Instead of assuming that technological civilizations should announce themselves across the galaxy, it becomes clear that distance suppresses visibility. Civilizations may remain effectively isolated, each confined to a small region of space-time, unable to broadcast their presence beyond a limited radius. In this context, silence is not evidence of emptiness. It is the natural outcome of separation enforced by physics. This perspective carries a sobering implication. If distance filters communication so effectively, then each civilization's understanding of the universe may be shaped almost entirely by observation rather than interaction. Knowledge accumulates locally, with little opportunity for exchange across vast separations. That realization leads to a broader conclusion. Light years do not merely separate stars. They partition experience itself, shaping what can be known, shared, and remembered on cosmic scales. Communication is not the only domain constrained by light-year distances. Physical travel encounters limits that are even more severe. While propulsion challenges are often framed as engineering problems, the deeper restrictions arise from energy, mass, and the structure of space-time itself. As speed increases, energy requirements grow disproportionately. Moving an object faster requires energy. Moving it much faster requires exponentially more. This relationship becomes extreme as velocities approach the speed of light. Unlike everyday motion, where increases in speed demand manageable increases in energy, relativistic regimes behave differently. Mass resists acceleration more strongly as speed increases. Each additional increment of velocity requires more energy than the last. At high speeds, this resistance becomes dominant. No matter how advanced propulsion technology becomes, accelerating massive objects toward light speed encounters an asymptotic barrier. the energy required increases without bound. This is not an engineering limitation that can be solved with better materials or more efficient engines. It is a structural feature of physics. Time dilation introduces an additional layer of complexity. As velocity increases, time passes more slowly for the traveling object relative to a stationary observer. This effect has been measured experimentally and is well established. For travelers moving at extreme speeds, their subjective experience of time compresses relative to the outside world. At first glance, this appears to offer a workaround. If time passes more slowly for the traveler, then long journeys might feel short. However, this does not remove distance. From the perspective of the departure point, the journey still takes years, decades, or centuries. Communication remains delayed. Coordination remains impossible. The traveler may experience less time passing, but separation persists for everyone else. Faster travel shifts consequences rather than eliminating them. The traveler may arrive having aged only slightly, but the origin civilization will have moved on. Generations may have passed. Political systems, cultures, and technologies may be unrecognizable. The journey trades physical distance for temporal dislocation. This exchange carries a cost. Travel across light-year distances with massive crews introduces the concept of generational ships. These are not vehicles in the conventional sense. They are self-contained societies designed to persist for centuries or millennia while in transit. The challenges involved are not limited to propulsion. Psychological constraints become dominant. Extended confinement, isolation from a home world, and the absence of a clear endpoint within a single lifetime alter social dynamics. Motivation must be sustained across generations that did not choose the mission. Identity shifts from exploration to survival. Biological uncertainty compounds these issues. Closed ecosystems must remain stable for durations longer than any controlled human experiment. Genetic diversity must be preserved without external input. Medical challenges must be addressed without resupply or evacuation. Even small failures compound over time. These uncertainties are not speculative. They reflect the limits of long-term biological and social stability in isolation. Slowing time for travelers does not eliminate these constraints. It merely changes who experiences them. A crew that arrives having aged little may do so into a future that no longer resembles their point of origin. The cost of speed is separation, not just in space, but in continuity. At this scale, travel becomes a trade-off rather than a solution. Faster velocities reduce subjective duration for travelers, but increase disconnection from origin societies. Slower velocities preserve synchronization, but extend lifetimes beyond biological limits. There is no configuration that eliminates distance entirely. This reveals a deeper truth. Light-year distances are not just far. they are functionally prohibitive for sustained human travel in any familiar sense. Movement is possible in principle, but connection is not. Presence can be achieved, but participation cannot. The implication is not that exploration is meaningless. It is that the cost of traversal must be understood honestly. Travel across such distances reshapes who travels, who remains, and what continuity means. With this understanding, the focus shifts again, from physical reach to conceptual reach. If travel and communication are constrained, then the primary human interaction with the universe becomes observation, understanding, and interpretation. That is where the final perspective emerges. Isolation does not erase meaning, but it changes where meaning is found. Once distance becomes time, separation stops being a matter of travel alone. It becomes a constraint on interaction. At interstellar scales, the primary limitation is not propulsion or engineering. It is communication. Every signal, regardless of medium, is bound by the speed of light. Radio transmissions, laser pulses, and any other form of electromagnetic communication travel at the same finite rate. As distance increases, delay becomes unavoidable. At short distances, this delay is negligible. Across planetary distances, it becomes noticeable. Across interstellar distances, it becomes dominant. This creates a fundamental barrier. Communication ceases to be interactive. A message sent across multiple light years arrives years after it was transmitted. Any reply arrives years after that. The exchange resembles correspondence rather than conversation. Feedback loops stretch beyond practical relevance. This delay forces a shift from reaction to prediction. On Earth, coordination relies on near-instant feedback. Decisions can be adjusted in response to outcomes. Errors can be corrected quickly. Across light-year distances, this model collapses. By the time information returns, conditions have already changed. Planning must replace reacting. Decisions must be made based on assumptions about future states rather than current realities. Systems must operate autonomously, handling unforeseen events without external guidance. Centralized control becomes ineffective because oversight arrives too late to matter. These constraints have direct implications for governance. Any society separated by light-year distances cannot be meaningfully managed from a central authority. Laws, policies, and directives would arrive years or decades after being issued. Enforcement would lag behind reality. Political contexts would change before instructions could be acted upon. Autonomy becomes inevitable. Remote settlements would be forced to make independent decisions, not by choice, but by necessity. Governance would decentralize naturally, driven by physics rather than ideology. Even shared origins would not prevent divergence. Over time, cultural drift would follow. Language evolves. Norms adapt to local conditions. Values shift in response to distinct environments and challenges. With delayed communication, alignment erodes. Shared identity weakens as generations grow up responding to local circumstances rather than distant influence. Distance enforces separation, not just in space and time, but in social development. To illustrate this, consider a hypothetical interstellar colony. This example is illustrative, not predictive. Imagine a human settlement established around a nearby star system, several light years from Earth. Communication with Earth takes years in each direction. A question sent today will be answered years later. Advice arrives after situations have already resolved or failed. In this context, coordination with Earth becomes symbolic rather than operational. Messages serve as historical records rather than actionable guidance. Governance shifts entirely to the local population. Over successive generations, the colony develops its own administrative structures, legal frameworks, and cultural norms. Not because of conflict or rebellion, but because delay makes external authority impractical. The colony's identity evolves independently, shaped by its environment and its isolation. Even if contact remains continuous, alignment does not. The physics of delay ensures that shared decision-making across light-year distances is impossible. What remains is exchange without synchronization. Information flows, but cohesion does not. This isolation scales with distance. A separation of a few light years already introduces generational lag. At tens or hundreds of light years, communication spans lifetimes. Messages become archival. The sender and receiver may never exist at the same time. At that point, interaction transforms into archaeology. Messages are received as records of past intentions from societies that may no longer exist in the same form. Planning across such distances loses coherence entirely. Civilization fragments into independent timelines. These limits are not failures of ambition. They are consequences of structure. The light year defines not only how far apart objects are, but how isolated they must be. It imposes boundaries on cooperation, governance, and shared experience that cannot be overcome by technology alone. Understanding this reframes the challenge of interstellar expansion. The question is not simply whether humans can travel far. It is whether meaningful connection can survive the distances imposed by physics. That realization leads to the final reframe. If isolation is unavoidable, meaning must be reconsidered, not as something derived from reach, but from understanding. That is where the scale of light years turns from limitation into perspective. Understanding distance in light years does more than redefine astronomy. It alters perspective. at the level of priorities and time horizons. When scale is fully accounted for, certain assumptions about urgency, conflict, and importance begin to shift. At human scales, conflict feels immediate. Disagreements, competition, and short-term pressures dominate attention because they occur within familiar temporal windows. Outcomes unfold quickly. Consequences appear proximate. Decision-making is optimized for immediacy rather than endurance. Cosmic scale disrupts this framing. When distances are measured in light years and timelines in millennia or longer, immediacy loses its privileged status. Events that feel urgent within days or years occupy negligible spans when placed against astronomical timescales. This does not render them irrelevant, but it changes how they are contextualized. Conflict becomes local rather than defining. Disputes unfold on a single planet within a single era. From a broader perspective, they are transient conditions rather than permanent features. Entire political systems rise and fall during the time it takes light to travel modest interstellar distances. What feels decisive in the moment often leaves no lasting imprint at larger scales. This perspective encourages long-term thinking. Light-year distances enforce delay, patience, and planning. Outcomes cannot be corrected quickly. Errors persist. Systems must be designed to function over extended durations without constant intervention. This logic, when applied inward, promotes stability, resilience, and foresight. Short-term optimization gives way to durability. When future conditions cannot be predicted precisely and feedback arrives slowly, robust systems outperform reactive ones. This principle applies equally to space exploration, infrastructure, and social organization. Emphasis shifts from immediate gains to sustained functionality. The contrast between immediacy and endurance becomes clear. Human societies are accustomed to rapid response and continuous adjustment. Cosmic constraints demonstrate that some environments do not permit such flexibility. Success under those conditions depends on preparation rather than reaction. This realization has implications beyond astronomy. It suggests that expanding temporal awareness can reduce the intensity of short-term conflicts. When actions are evaluated against longer horizons, priorities adjust. Cooperation becomes more valuable than dominance. Preservation becomes more important than acceleration. Light years do not impose this perspective directly. They reveal it indirectly. By confronting the scale at which the universe operates, viewers are invited to reconsider the scale at which decisions are made. The contrast between cosmic duration and human immediacy exposes the limitations of short-term thinking without dismissing its necessity. The result is not detachment, but calibration. Understanding scale does not demand indifference. It encourages proportion. It allows immediate concerns to be addressed without mistaking them for absolute determinants. In this way, cosmic perspective supports rather than undermines meaningful action. With this shift in place, the narrative reaches its conclusion. The final task is to consolidate the insights gained and leave the viewer with a stable, reflective framework that integrates limitation, understanding, and responsibility. Understanding light years begins as a technical exercise and ends as a philosophical reckoning. What appears at first to be a unit of astronomical bookkeeping reveals itself as a framework that reshapes how distance, time, limitation, and meaning are understood. At the most basic level, a light year is a measurement. It is a precise, physically grounded unit defined by the speed of light and the passage of time. It exists because smaller, human-centered units fail when applied to cosmic scales. Light years make distance legible, where kilometers and miles collapse into abstraction. But a light year is more than a measurement. It is a constraint. Each light year represents an irreducible delay, a minimum separation enforced not by technology, but by the structure of reality itself. No signal can cross it instantly. No object with mass can traverse it without consequence. It defines the maximum speed at which influence, information, and causality can propagate. Beyond that, a light year functions as a historical lens. To look outward is to look backward. Observation becomes delayed information. The universe does not present itself as a synchronized whole, but as a layered record of events spread across time. Stars, galaxies, and cosmic structures appear not as they are now, but as they were when their light began its journey. Distance and time merge operationally, transforming astronomy into a study of history written in photons. At the largest scales, light years form a civilizational boundary. They limit communication, coordination, governance, and shared experience. They ensure that civilizations, if they exist elsewhere, develop independently, shaped by local conditions rather than collective oversight. They prevent real-time cooperation across the stars and enforce autonomy not by choice, but by delay. Light years do not merely separate locations. They partition experience itself. Taken together, these roles redefine how humanity fits into the universe. From a purely spatial perspective, humanity is small, confined to a single planet, orbiting an ordinary star, in a typical region of a vast galaxy. From a temporal perspective, humanity is brief, existing for a fraction of a second when measured against cosmic timescales that stretch billions of years into the past and future. From a physical perspective, humanity is limited, unable to reach most of what it can observe, unable to cross distances that it can measure with extraordinary precision. And yet, These limitations do not erase significance. They clarify it. Humanity is small in scale, but significant in capability. The same species constrained to a narrow region of space has developed the tools to measure distances trillions of kilometers away, to reconstruct events billions of years old, and to model regions of the universe it will never visit. Humanity is limited in reach, but expansive in understanding. Physical access is restricted, but conceptual access is not. Through observation, mathematics, and inference, local beings extract global truths. They map structures far beyond their immediate environment, using laws that apply everywhere. Humanity is isolated, but not ignorant. Light years prevent contact and coordination, but they do not prevent comprehension. Knowledge does not require presence. Meaning does not require expansion. This resolves a common tension. Cosmic scale can feel diminishing. It can provoke a sense of insignificance when human concerns are placed next to galaxies, deep time, and vast emptiness. But that response assumes that value scales with size or dominance. It does not. Value emerges from awareness, the ability to recognize limitation, to measure it accurately, and to reason within it is not trivial. It is rare. Within a universe that operates blindly according to physical laws, understanding is not guaranteed. It is an achievement. Light years sharpen this realization. They show that the universe is not designed for convenience, that distance is real, delay is unavoidable, and reach is constrained. They remove comforting illusions of immediacy and accessibility. They force an honest accounting of what can and cannot be done, but they also reveal something stabilizing. Even within strict limits, there is room for depth. Even without expansion, there is room for meaning. Even when separated from everything else by immense distances, understanding remains possible. This perspective encourages proportion rather than despair. Short-term conflicts and immediate pressures do not disappear, but they are contextualized. They occur within a narrow band of space and time. They matter locally, but they do not define the whole. Long-term thinking becomes more visible. Durability, preservation, and foresight gain relevance when placed against scales where feedback is slow and consequences persist. Understanding distance does not make the universe feel smaller. It makes awareness larger. It expands the frame within which choices are evaluated. It reveals that limitation is not the same as futility. That isolation does not negate meaning. That being unable to reach everything does not prevent understanding much. The light year stands as a reminder of this balance. A reminder that humanity occupies a modest position in a vast structure, yet possesses the rare capacity to comprehend that structure. That it is constrained in movement, yet expansive in insight. that it is separated from most of the universe by insurmountable distances, yet connected to it through the laws it obeys and the light it emits. This is not a call to minimize human experience, nor to inflate it. It is an invitation to see it clearly, to recognize that we live in a universe we can measure far beyond what we can ever reach, and to consider, carefully and honestly, what does it mean to live in a universe we can measure far beyond what we can ever reach?